Welcome back for theme 3.4, where we will be learning about Green's theorem and what a great thing it is to have. So Green's theorem says that if C is a piecewise, smooth, positive orientated, simply closed curve, D is the region bounded by C. So D is this piece. If P and Q have continuous partial derivatives on an open region that contains D, then we can write our line integral as a double integral, which is described by the area of D. Basically, when you know that you can use Green's theorem, is if you have a closed curve that is positively orientated, so it goes counterclockwise. And if the partial derivatives of P and Q are continuous in the region. So those are the two things that you have to look out when using Green's theorem. It just makes life a lot more easier when you have four different curves and it creates a closed curve, and then you can just use your area that is bounded by the curves to describe your line integral. So, examples. Determine this line integral with C the rectangle. Okay, so this is our region. So note that if we didn't know about Green's theorem, we would have four different curves. 1, 2, 3. and 4. So you would have to do 4 different line integrals to actually get this line integral. But now we know of Green's theorem and life is better. So questions we have to ask ourselves before we jump into using Green's theorem is the curve positively orientated? Yes, it is, because it goes counterclockwise. Is it a closed curve? Yes. And lastly, is our partial derivatives of P and Q continuous in this region? Which they are. So now we can use Green's theorem. So this is what it would have looked like. You just say 2x minus 3, which gives you 2x plus 3. And then your boundaries, you can either use y or x, type 1 and type 2. So our boundaries for y is from 0 to 4, and our boundaries for x is from 0 to 2. And this will be your integral. And then you just integrate towards x and y, and you will get the following answer. So it's much easier and quicker than getting 4 different line integrals. Agree? If we want to get the area of the region, we have to come up with some interesting values for P and Q, because sometimes you do not want the line integral, but you just want the area of D by using Green's theorem. So if we want to get the area of the region, we need to choose values for P and Q so that Qx minus Py is equal to 1. Possible choices of P and Q include, if we say P is 0 and Q is equal to x, because then if you take the partial derivatives, Qx or Q partially derived towards x would be equal to 1, and P partially derived towards y it's just 0. So Qx minus Py will be equal to 1. And you could also use P is equal to negative y and Q is equal to 0. And the same, you can come up with different equations for P and Q. As long as it equals to 1, then you will get the area of D. An example, they ask, find the area of the ellipse using a line integral. So usually you could just use a double integral and just get the area of the ellipse. But if they ask you to use a line integral, you have to think about what your P and Q values for your vector field will be. So our area is x dy, because we chose q to be equal to x, so it works out. So either you can use Green's theorem, or you can get a parametrized curve. So to get the parametrized curve, you just say it's an ellipse. So it'll be 2 cos t, 4 sin t, which you will get from these equations. And then you can get your r prime of t, which is -2 sin t and 4 cos t. And then you got the r prime t because you need the dy. So then you fill in the x with the x function in terms of t and the dy, which comes in for 4 cos t, and then dt. So since we have a full ellipse which goes counterclockwise, we just say it goes from 0 to 2 pi. So then we would get the following, and you can just integrate that and get 8 pi. We can now determine the line integral of a vector field in 3 different ways. So you can do it the normal way, where you just parameterize your curve and you get r prime of t, and you put the equations for x, y, and z into your vector field, and then you just find your line integral. When f is conservative, we can find our potential function and use the fundamental theorem of line integrals and get our line integral. If the curve that we're working with is closed and in the positive direction, and our partial derivatives are continuous on the region, we can use Green's theorem to get our line integral for the vector field. So I hope you learned that Green's theorem is such a great help, and this is the end then for the theory part of theme 3.4. See you at the practice session.